السلام عليكم، أنا رامي طيبة
وأنا ساري صبان،
وهذا بودكاست علم اف ام، البودكاست المهتم بآخر أخبار العلوم من فيزياء وكيمياء وأحياء والشلة الباقية. هذه الحلقة رقم 39 المسجلة يوم 11 فبراير 2016. 17 واو. طيب ما مشكلة، كمل. الشو مست جو اون. كيف حالك يا ساري؟
الحمد لله تمام.
اليوم عندنا حلقة خاصة جدا، عندنا ضيف.
مظبوط، أخيرا لقينا أحد للكوانتم فيزيكس
أخيرا. بس حيتكلم بالإنجليزي.
ساري.
عشان ليش كده يا عبد الرحمن؟ قول لنا بالإنجليزي.
Because English is my first language originally. I was raised in the US. I've lived there for half my life and I struggle a lot with Arabic.
أنا أتخيل برضو إنه بالذات يعني لو تتكلم أنت إنجليزي لغتك الأولى وبتتكلم شيء تقني وعلمي جدا، مرة صعب يعني تعرف كيف.
ايه انا واجهت نفس الصعوبه لما رجعت من بريطانيا برضو، لانه تعليمي تقريبا في الاحياء كله كان بالانجليزي، والاول ما رجعت هنا لقيت انه الناس ما بيفهموا الانجليزي، حتى يعني احنا في الجامعه برضو بندرس بالانجليزي بس الطلبه ما بيفهموا المصطلحات، فاضطريت اتكلم واستخدم المصطلحات العربيه، فكان في البدايه صعب بس بعد فتره تلاقيها سهله.
لا هو حتى في بدايه لو تسمع حلقات علم اف ام اللي في البدايه،
اي صح، حتى هنا في علم اف ام برضو في البدايه كده
كنا صعب يعني كل ما نواجه مثلا كلمة معينة quantum physics يعني ما كنا نعرف إيش معناها، ولقته وطلعت والله هي الفيزياء الكمية. ف يعني maybe أنت ممكن تهتم في الموضوع ده إنك تبدأ إيش
يمكن في المستقبل
هتبدأ تخش هنا بالجامعات اللي هنا.
هتلاقيها أسهل مرة لو أنت قاعد تتكلم مع الناس أو تواصلت معهم بالعربي، هيفهموك بسرعة.
طيب انت قول لنا ايش انت، مين انت، ايش تسوي في الحياة؟
أنا عبدالرحمن لنجاوي. I go by Lingo. I've been a student of science my whole life. It's a thing that I just enjoy, I'm passionate about. And I just come back from the US and have a ton of accumulated knowledge I'd like to share.
What were you doing in the US?
I was studying everything. Like literally, I started off engineering, and then I took a year of political science and sociology, and then another year of photojournalism, and then I ended up just traveling across the U.S. until I just realized that, maybe it's time to come home and, share what I've accumulated before I go off again.
Go off to where?
The rest of the world.
Okay. طيب, where does quantum physics fit in?
Quantum physics is how I was introduced to loving science, like which science in particular I wanted to delve into. I've always wanted to be a scientist. I've always been very technical and very, pedantic, and I pay a lot of attention to detail, and things always had to make sense. Things always had to be logical. There always had to be an explanation for things. I was never just satisfied with the brush off answers of it is because it is. No, I need to know why is it that way? Why is the sky blue? Why is the sky blue? And how do airplanes fly? And what am I made of? And how long did it take the universe to make me? And I was fortunate enough to be introduced to a number of people who were as passionate as I am now, but for much longer. And they helped guide me into into physics in specific, and with their help I was able to hone my knowledge and skill in understanding how things work. And to me right now, just thinking in physics is second nature.
Excellent.
So let's get into quantum physics. Quantum physics or quantum computing, or both?
So quantum computation is a result of quantum physics, similar to how cell phones and laptops are a result of electrical engineering, or as a result of like fields and electricity and stuff. So quantum computation is an application that the world has been trying to get right, and it still is like one of the holy grails of physics and and IT to produce an efficient computer that uses atoms instead of transistors and phases between atoms instead of transistors. So like in regular computers with binary, you have zeros and ones. With quantum computation, you have 0 or 1, or 0 and 1, or everything in between and everything in between, all simultaneously. So I think I read somewhere that one atom is equivalent to like 30,000 transistors.
Wow.
Wow, amazing.
Yeah.
So we're talking zeros and ones من ناحية
Binary and how like how the computer, how the processor interacts with the hardware to give you something on the at the terminal.
Okay. So we can do a lot more operations this way in one atom. You can fit a lot more. Like right now we have a chip that has X amount of transistors right now, and if we actually get to this holy grail, we will be able to do 30,000x.
Yeah.
Okay.
Yeah.
Are you familiar with Moore's law?
Exactly. I was just about to say Moore's law doesn't take into account quantum computation. Because Moore's law, so Moore's law, for those who don't know, is a dude, like based on his observation, says that every year the number of transistors in a computer will like double, I think, or something.
Every 18 months.
Every 18 months, and that our survival depends on the integration of our real lives with information technology. So think of the hybrid the AI human hybrid is essentially where he's trying to get to. And with quantum computation, I mean, right now we all know that our brains are much more advanced than modern day computers. Quantum computation makes our brains obsolete.
We discussed this last week, where we were talking about artificial intelligence to diagnose skin cancer. So we're seeing this progressing and happening at the moment.
Yeah, so imagine an atom that's also a processor and a CPU in general, and then imagine nanotechnology, where every tiny little, molecule-sized robot with a supercomputer inside it, trying to find, where the cancer is, trying to, support your white blood cells, or trying to see why your car has oil leaks, or trying to, prevent airplanes from malfunctioning mid-flight. So, like, it's applicable everywhere. And the more attention we give it, the more love we give this tiny child right now, the better it'll be when it grows up, and the more beneficial to humanity. But simultaneously, you got to consider that all mad scientists are not mad scientists, but the people who fund them might be mad. And
what does that mean?
That means E = mc squared could, fuel the sun. E = mc squared with the same protocol can fuel the planet, but it could also destroy Hiroshima.
Yes. Okay.
Let's delve into quantum physics. So for our listeners, quantum physics is the physics that is...
So there are two types of physics. There's quantum physics, and then there's relativistic physics. All the physics that we know and hate is relativistic physics. Newton, from Newton to Einstein. How the table stays in place, how the Earth is attracted to the sun, and how electrons move with one another. Forces in general is all relativistic physics, because it's one object relative to the other, to the other, and you need to have a point of reference, and it's a mess if you're taught it in a messy way. Quantum physics, on the other hand, this is where things are more interesting and logic gets thrown out the window, because quantum physics is how the insides of atoms interact. and how things that aren't atoms interact, and what we can do with that, such as the quantum computation. Quantum computation is insane, relativistically speaking.
At the moment, as I understand, scientists are trying to build the standard model, and the standard model is.
The standard model is basically the table of elements on a smaller scale. You have several families of subatomic particles, gluons, charms, quarks, all of these really, really interesting things. And fun fact, most of the people who named these are very much into Dungeons and Dragons, and that's why you'll find all of the references here and there. Also, we're all science fiction geeks, and photon torpedoes are basically flashlights. So pay attention to that next time you're watching Star Wars.
So quantum physics is the physics beyond the atom, or everything that is smaller than the atom. So, for example, we know the atom is made of protons, neutrons, and electrons. But what is a proton made of? So,
all right, before we get into that, we have to discuss the 4 fundamental forces. I'll start with the weakest. Gravity. Gravity dictates that all matter, however small or large, however far apart, is attracted to itself and other matter, and accelerates in that direction. Next, you have electromagnetism, which is how atoms interact with one another through electrons, charges, covalent bonds, etc. It's the chemistry that we know, as well as electronics. Next, we have 2 forces that are relative to one another. They're relatives of one another, and both of which are the nuclear force. The first, the weak nuclear force, is atomic weaponry, and that's just the weak nuclear force. It's the force that holds protons and neutrons together. Okay, and the force there can be calculated using E equals mc squared, where the energy within an atom still has a calculable mass. So if you have uranium-238, it weighs more than uranium-235 plus 3 neutrons.
Well, exactly.
And then you have the strong nuclear force. And this is the one that, in 2012, everyone was afraid CERN might destroy the universe. I'll get to that in a sec. So the strong nuclear force is what holds protons together, what holds neutrons together.
I'm sorry, so the weak nuclear force holds...
The weak nuclear force holds a nucleus together. It's why protons and neutrons can hang out.
All right.
But a proton itself and the neutron itself, they're both composed of subatomic particles, subnucleic particles. And this is where quantum physics comes in. Now, these particles are held together to form a proton or a neutron by the strong nuclear force.
Okay, so...
And that also can be calculated using E equals mc squared.
All right. So a proton is made of quarks, as I understand. And as you said, they have very funny names. So the type of quarks that we've discovered so far, I'm not sure if there are more to discover or not. I'm not in the field, but so far they are the up quark, the down quark, the charm quark, the strange quark, the top quark, and the bottom quark.
Yeah, there we go.
But a proton...
This is the difference between physicists and biologists. We call them for what they are. A black hole is a hole that's black. A solar storm is a storm that's solar. We don't have super intricate Greek and Latin names for dogs.
So a proton is made of 2 up quarks and 1 down quark.
And a neutron is the opposite.
Exactly. And they're held together by another subatomic particle called the gluon. So at the moment...
Which glues them together.
Exactly.
Hence the word. I'm dead serious. Positrons and electrons, one is positive, the other is electricity.
We don't have time for naming.
I know.
Just what it is and move on.
Exactly. And it's so much easier for the next guy.
So the standard model at the moment, as I mentioned, there are the 6 quarks, and then the leptons. So we've got the electron neutrino, the muon, the muon neutrino, the tau, and the tau neutrino. And then you've got the, how do you pronounce it? Gauge or gauge bosons?
They're bosons generally. Okay, so there are 2 types of... so if anyone's paid attention in chemistry, we learned about, spin of a particle. And some particles spin at an integer spin, so they spin at like 1 rotation or 2 or 3. Others do multiples of halves, so half and 1.5 and 2.5.
All right.
One of them is bosons, the other is fermions. But here you're talking about, I think it's gauge bosons, which includes the Higgs, I think.
You've got the gluon, the photon, the Z boson, the W boson, and the Higgs boson.
There we go. The Higgs is, it kind of made big news a couple years ago when CERN, the Center for European Nuclear Research, between Switzerland and France, this was the Atlas experiment, which everyone thought was going to destroy the universe. So let me talk about the Atlas experiment real quick, and this is what's going on in quantum physics right now. So, there's something called a particle accelerator. In Switzerland, it's called the Large Hadron Collider, and hadrons are, you'll find it on that page somewhere. What they did is they charged hydrogen atoms, which are basically a proton being orbited by an electron. So by charging it positively, you're simply just removing the electron, and all you're left with are single protons.
Yeah.
And they charged a handful of these, and they shot them in opposite directions at like 90% the speed of light. And the Large Hadron Collider is a circular tunnel. It's actually the largest man-made circular tunnel in the world, 27 kilometers in circumference, and an entire Burj Khalifa underground. If any of you have read Angels and Demons by Dan Brown, it's kind of set there, and he talks about antimatter and stuff, which again we'll get to later. So sending protons at very close to the speed of light in opposite directions will eventually lead to a collision. Again, collider. And the whole tunnel is really, really, really big. I was almost offered an opportunity to go and check it out, but unfortunately someone else took the seat. And the whole tunnel is sensors and computers and magnets and electronics, and what they were trying to do is they were trying to calculate how much energy is ejected from that collision, because they know how much mass they're shooting in, and E equals mc squared, so you're supposed to know how much energy is going to be produced by that mass. And some energy went missing, which scientists predict it either went to like a different dimension, or it just changed into something that we couldn't detect. And then there was some energy that was unaccounted for initially that we found. And among all the calculations, we found something called the Higgs boson, which scientists often refer to as the God particle. It is the particle that gives protons and neutrons mass. Like how if you were to throw something into a pond, it either gets wet and soggy, or it doesn't. That's how fields work, like the electric field, the magnetic field, the gravitational field, etc. And some things, you walk through a field and you feel nothing. Like if there's a magnet and you walk through a magnet, like at the airport, when you're going through, security and you're walking through the metal detector, you don't feel it. But that doesn't mean it's not there. Whereas if there's metal and you're at the you're getting a CAT scan or an MRI or something, and you have like a metal watch, you're screwed. So you won't feel it, but the metal will, which means the metal reacts to the field. Of all the fields that there are, and there are many, and that's basically what quantum physics studies. The Higgs field exists all over the universe, but only particles that interact with the Higgs boson or have the Higgs boson within them actually interact with the Higgs field. The Higgs field is what we consider to be real life and everything else to be virtual and mathematic. So it's what gives mass to things. It's why we have things. It's matter as opposed to pure energy, such as neutrinos, for example. They don't have to worry about this. They don't have to worry about things in their way. We receive roughly 60 billion neutrinos per second per square inch on the planet Earth from the sun. But you know what happens to these neutrinos? They go right through. It's as if Earth doesn't exist because they don't interact with Higgs.
No, the neutrinos are being produced from the sun, right?
Yeah.
And they don't interact with us because of their...
Because they're neutral. I mean, a neutrino, so you have protons, positrons, electrons, neutrinos, and a couple other things.
Yeah.
And these don't interact with the Higgs boson. And so they don't really have mass. They have energy, but they don't have... and therefore they have mass according to E equals mc squared, but they don't interact with the mass of other objects. They're not attracted with gravity. You could have two electrons on the other side, on different sides of the universe, but they're not attracted to one another in a gravitational sense.
So how did they discover them? I know how they discovered them, but explain to us, how did they discover the neutrino?
Could you tell the story? Because I might be a little...
They discovered it through water. That's what I understood. I'm not sure if it was somewhere in Switzerland or in Japan, but they made these large, absolutely pure tanks of water, and the details afterwards are fuzzy for me. So I don't understand if did they see photons coming out of it, or did they see a difference in mass? Something happened that made them discover the neutrino.
Well, I honestly am not very familiar with the story, but what I can tell you is neutrino detectors. Have you ever seen the movie 2012?
Yes.
Yeah, so you know at the very beginning when the dude was the Indian scientist was freaking out because, there are way too many neutrinos or whatever. So what happens in these super underground, super, controlled environments with pure distilled water, which is just H2O, is it's very easy to control. And so any change is significant and noticeable. And honestly, I don't really know how neutrinos would interact with them, but that's the explanation of how the apparatus works.
Yeah. The amazing thing is that it can, as you mentioned, there are billions, trillions of neutrinos that pass through us every second, but they detect one. So if one somehow interacts with a water molecule, they detect that particular particle.
Well, again, a controlled environment means you also have a lot of sensors to see what's up.
No, but it shows you the advancement in technology that we can actually detect a single particle, a subatomic particle.
A couple of years ago, physicists at MIT were able to film a single photon.
Yes, yeah.
Which is, for those who don't know, it's a light particle. So light, we all know, comes in waves, and thanks to Newton, we understand what colors are. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, although indigo doesn't really count, but he was just obsessed with the number 7, as was Copernicus. But anyway, we know that each frequency of these light waves gives a certain color, and the majority of light waves we can't see. But simultaneously, there's something called the particle wave duality, which quantum physics again. It says that particles can interact with the apparatus detecting them, either as waves or as particles, depending on what you're looking for. And so a single photon is essentially a single wave of light. And the energy in it is the main counting unit for energy, which is 1 quanta, and hence quantum physics.
Now let's talk about spin. This is a subject in quantum physics that is very confusing for me.
Okay.
Because using spin, as I understand, as you mentioned, several particles have specific types of spin, and I'm not sure, but as you can change the spin.
You can change the direction of the spin.
Direction of the spin, yeah.
But you can't really change the spin, at least not yet. We don't know what the future holds. We used to say that the Earth was flat, but then we discovered it wasn't. We used to say that we were the center of the universe, and then we discovered we weren't. And now we think there's one universe, and who knows what the future holds. So just because we can't do it now doesn't mean we won't be able to do it in the future. But anyway, again, Bohr's theorem says that you need to apply a certain number of electrons within their orbitals before you can move on to the next orbital. And the way they're organized is by spin. They don't interfere with one another because they're spinning in opposite directions. And that depends on a number of other variables, such as what orbital it's in, how much energy is in it, which determines what orbital it's in, and you can adjust that by shooting photons into it. Again, just shooting quantas of energy to make it jump either up an orbital away from the nucleus or down an orbital into the nucleus. And yeah, back to quantum computation. It's the spin of the electron that does the computation. It's either up or down, but at a certain temperature. It doesn't have to be limited to either up or down, and you could just set it at whatever degree you wanna use it at.
Oh, interesting.
Yeah, so the state is basically represents the 0 or 1.
Yeah, but you have that much more adjustment.
Yeah, so one state 0 or 1 is this is 1 bit, but with a quantum computer, you can have multiple bits,
and you can have
thousands of bits, I'm guessing,
and thousands of bits within the same atom, the same atom, and then simultaneously. It's not either on or off. It's on or off or both or anywhere in between. Mm-hmm. And that will open up, an entirely different world of computation. Once we have quantum computers that are readily available for the everyday man, we're gonna look at these computers. We're gonna look at Shaheen at KAUST as one of those old Chinese bead calculators. It's obsolete. It doesn't matter anymore.
Abacus.
Yeah.
Even worse, like right now, if you look at computers in the 80s and like, what the hell is this?
Like the big room computers that use, those scan cards back in the 60s.
These computers will look even worse, probably.
And iPhones.
So how far are we from this?
We're as far as the political will, keeps us. Because realistically, we have the technology, we have the trajectory, we have the momentum. We need the funding. And a lot of this stuff is extremely expensive. It takes up a lot of energy. So we need, sources of energy. And a lot of us on the scientific side of things don't very much enjoy using coal or fossil fuels. So we need clean energy. And to do that, we need a lot of money. And we've developed it to the point that it can be very cheap. The sun gives us 125,000 terawatts of energy every day. The International Energy Association calculated that all of humans on Earth in 2013 combined use less than 1/10,000th of that amount of energy. So if we can harness the energy coming from the sun, we wouldn't need most of the fossil fuels, and we can build these solar panels using the very silicon that the desert provides. And so the desert can be our battery.
Yeah.
So if we harness that, and if we are given the authority and given the proper apparatus, just by being given the proper funding, we can have quantum computation by the end of the decade.
Okay, I wanna go back to a remark you gave earlier when you said that you equated quantum computing and quantum physics or quantum computing to Oppenheimer opening Pandora's box with nuclear power or nuclear bombs. How is that? Well, how does the analogy work here?
Okay, the analogy was nanotechnology, AI nanotechnology with supercomputers in it. You could either use it to cure cancer, and clean the waters and, reforest the earth and protect species. And for those species that are extinct, but we need for the biosphere, for the ecological balance, we can replicate and maybe even make better. Or we could use it to poison the water supply, destroy all forests, and then
why would we do that? I mean, a nuclear bomb, yes, okay, there's a war, we're going to drop it on a few countries that we hate, we don't like.
The thing about
why would we?
The thing about nuclear warfare is we've advanced to a point that it is illogical to destroy a country.
No, I know, I understand that part of it.
When you can destroy only those who oppose you and keep the country and its wealth intact. So, for example, right now we're at war as Saudi Arabia, and we're terrified that, what if our enemies destroy our oil supply? What if, our enemies target our schools or universities or, places where there are a lot of people? They don't need to do that. There are 7 desalination plants. If you disable any of them, the whole country is in a lot of trouble, and the wealth is intact, the infrastructure, whatever there is here, is intact, and the banks are still functioning. We're all still functioning. We're all still working. But that's the fear with artificial intelligence and nanotechnology and just advancing into the unknown. This is the fear of the scientific community.
Getting Skynet?
Yeah.
I always believe that science is a double-edged sword.
Exactly.
Whatever you discover or whatever you learn in science, you can use it for good or for bad at the same time. Which is why I'm always opposed in teaching science in its raw form. Because some people, I'm not. Sorry, I said that wrong. I'm opposed to people who prevent teaching science in its raw form. Exactly. Because some people argue, no, this science can be used for mischievous things. I always think that humanity would usually move towards the good side of science, and just a minority of us would go to the bad side for whatever reasons. And so I believe science is a double-edged sword. As you said, so quantum physics was used to develop a nuclear bomb, which is extremely destructive, but at the same time to develop nuclear power, which is the cleanest form of energy we have so far.
Thus far, yeah. Not really, because you still have all that nuclear waste, and eventually what happens is that it's either thrown into Ethiopia or South Africa, buried underground. NASA tried sending some to throw into outer space, but Apollo 13, Challenger, and Columbia kind of, said that it's too big of a risk to have a lot of nuclear waste possibly go up in smoke right above the atmosphere, poisoning everybody.
There's a fine line in this argument. One thing people can argue is that coal, petroleum power development actually poisons or releases a lot of pollution into the atmosphere, while nuclear power does produce nuclear waste, but it's kind of contained.
Yeah, it's contained, except the nuclear waste doesn't get neutralized until like 10,000 years from now. So it may be contained today, but you don't know what happens when an earthquake comes and attacks, that particular part in which you buried everything.
It's true, and we have the second law of thermodynamics, which is entropy, which means if you do put order into a system, which means you take all these quantities of nuclear waste and you store them into barrels, these barrels will eventually rot away.
It's
and
PV equals NRT. Yeah. And
we talked about was it research like a few weeks ago or an experiment? Yeah. Was it an experiment that this nuclear waste they convert to diamonds and use as batteries?
Yeah, so you don't know, you might find use.
Yeah, you could recycle, reduce, reuse, and recycle. That's excellent, and I'm so totally on point with that. But simultaneously, I also got to consider what if something goes wrong? You look at Chernobyl, and Chernobyl is like the go-to reference here. But more than Chernobyl, look at Fukushima. Mm-hmm. Fukushima has poisoned salmon all the way to California. Mm-hmm. Yeah. What if something goes wrong?
Going back to quantum computers, So we talked about the quarks, which is okay. Conceptually, it's easy to grasp. You know, you've got a proton, and inside it there are quarks and other subatomic particles. But the real difficulty in quantum physics is some of the laws. For example, the
uncertainty principle,
Heisenberg uncertainty principle,
the exclusion principle, and Schrödinger. Those are the three big ones. So let me put it this way. You're in a car, right? Mm-hmm. And you're driving on a highway, and the highway splits into three, like you can either go straight or take one of the two exits to your left or to your right.
All right.
You close your eyes, and a second later, you're not dead, which means you've taken one of the three, but you don't know which, right? The uncertainty principle it says that you can only tell the velocity, the momentum, or the velocity of a particle, or its location. Okay, either because if a particle is moving, then it doesn't have one location, and if a particle is in one location, therefore it's not moving. So you can't do both. You can only estimate with a specific number of certainty or uncertainty. So here, you're certain that you didn't die, right? So you're not stationary. You're still in motion. That's what you're certain of in the analogy that I'm making. Okay. Next is the Pauli exclusion principle.
Just one moment, just to summarize, because I understood it in a slightly different manner. I understood it that when you try to observe a particle, you can only observe it, sorry, you can only measure the particle without observing its location. So the act of measuring a particle changes its place. So you can't measure it and find its place at the same time.
So you know the mass of the particle, okay? Momentum is mass times velocity. The way you're going to measure its momentum is by measuring the time it takes for the particle to go from A to B. Okay? You know it's at A, you know it's going to pass by A.5, and you know it's going to get to B. But you're not measuring where it is. You're measuring how long it takes to get from one point to the next. And that's how you get the velocity. And you multiply that by the mass, and now you have momentum. Right? Whereas to find its location, you're not concerned about its motion. You're concerned about where it is at the specific point in time. So T3, for example, as opposed to T initial, relative to T initial, the particle will be at point C. And you can only know one of these with a specific certainty, because again, unless you can reach down and pick it up, you're just running based on measurements by the apparatus that may or may not be faulty due to whatever.
And this is, as I understand, the main issue in quantum computing is you can't measure the quanta, as I understand, but
it's more than that. You can't really control a single atom at a time. There are a couple quantum computers scattered across the world. Specifically, there's one in Eastern Australia, I think. In order to build the building for that computer to be built in, the concrete is actually suspended on springs separate from the rest of the neighborhood. And then there's more and more insulation, all of which to prevent the vibration of the earth interfering with the apparatus. And then there's cryogenics going on, where you have to use lasers to freeze the molecules to move them in place, and then you have tons of magnets and computers and everything just to make sure that you know how to turn it on right. And then once you turn it on, that's a completely different experiment altogether, and you have to be extremely sterile, clean, and you can't really talk in the room, and it's really scary, and it's expensive, and it takes up a lot of energy, and all these things put together, as well as Donald Trump having a computer, means that why do we need to keep going?
Let's go to the Pauli exclusion principle.
The Pauli exclusion principle says that you can't have more than one particle in one place, and you can't have one particle in multiple places. So you know while you're in the car that you've taken one route. You don't know which one it is, right? You know that you've taken one route. You either went right, straight, or left. And you know you didn't take both of them, and you know that they don't merge, right? So that's the Pauli exclusion principle.
What about Schrödinger?
You don't know which route you've taken until you open your eyes and see what's around you.
Okay. And that's where the Schrödinger's cat comes in.
Exactly. The cat is both dead and alive until you open the box.
So for our listeners who don't understand the Schrödinger cat's example, Schrödinger says if you have a cat and a pot of poison and you put them both in a box, you cannot see the cat, and therefore you cannot determine if the cat is alive or dead. So you would assume that the cat is both alive and dead at the same time, and until you remove the box and find or determine for certainty if the cat is alive or dead.
This brings the question: if a tree falls in the forest and no one is there to hear it, does it make a sound?
Very philosophical.
Of course, it does make a sound.
Of course it does. And we've made a splash here, but we've ran the gamut. We need to wrap this up.
Two more concepts.
Okay. مرة مستعجل انت. Okay.
No, because
why don't we bring him again next time?
Maybe we should. Yeah. There's a lot of concepts in quantum.
We could have a part two. We could have a part two.
There's a lot of concepts we want to tell our listeners, because that's one of the issues we face here in Ilm FM, that a lot of research coming out from quantum physics that we kind of understand but we can't really explain, and we get confused in the middle and we don't understand it's كيف تقول محله في الإعراب. فهم علي؟
Sari يعني got the biology down. I got nothing down.
You got the computer science down.
Sort of.
You're the one who makes it happen.
Thank you. And yeah, so physics is our weak point.
Yeah.
Okay.
So the tunneling protocol, as we understand, one of the limitations for the Moore's law is, okay, mathematically it's easy to draw a graph, and you say every 18 months, you will get a double in the speed and the size of your computing power, because you get smaller and smaller transistors. And transistors basically an off and on switch. But we will reach a point where the transistor or the switch is so small that the barrier between on and off is so small, the electron can just pass through it.
That's where you get to quantum computation.
Exactly. But how is this possible? I mean, this is one of the core concepts in quantum physics that us normal people cannot understand. We can't understand how, if you bang your head through the wall how 100 billion times, at one point by chance you will go through the wall.
It's not that. He's saying it gets so small. So like you could bang your head through a wall, you could bang your head through a piece of paper, or you could bang your head through a one single atom thick sheet, and you'll just go through it. You know, I mean, we go through atoms all the time. Matter of fact, so if you look at like an atom, you think of the nucleus and you think of the electron orbitals around it. Well, to put that in perspective, the nucleus relative to the size of the atom is like you standing in the middle of al-jawhara. You're the nucleus and everything around you is the orbitals.
Al-jawhara is a stadium.
Al-jawhara
football stadium, just to
And
clarify that. Yeah. Okay.
And so over 99% of the volume an atom takes up is empty space. And so atoms can go through one another. You can, in theory, walk through a wall if all the atoms are aligned to allow you to do so. And when you have a thin enough wall, it'll pass through you as opposed to you passing through it.
Interesting concept.
And again, that's where quantum computation comes in and changes the game. It's the next evolution.
That's the limit. The quantum tunneling gives us the limit for silicon-based computers.
Yeah.
The last concept that I want to cover is quantum entanglement.
All right. So earlier I said that gravity works by connecting two particles within the Higgs field at any point in the universe. Quantum entanglement takes this one step further, where particles are created in twos. So if you have in your hand a proton, then somewhere else in the universe there is another proton. And if you tickle this proton and it giggles, the other proton will also tickle and giggle. It's like what we think about identical twins, how they both think alike and how they can read each other's minds wherever they are.
That's such a crazy concept.
Yeah, I mean that's like a huge breakthrough in communications.
Yeah.
Can you shed a little bit more light on like the consequences of getting to this technology? Or
like, what do you mean? Like
applications, not consequences.
Applications. Well, I'm not entirely sure, but a lot of people think teleportation. But some people have been thinking like teleportation. Like if I can clone the atoms in me with the quantum entangled duos of them somewhere else, then I can literally be in two places simultaneously. But Pauli's exclusion principle prevents that from happening, because not only is it applicable within particles, but like how on Earth or in the universe are you going to find two identical atoms, given two identical particles, two entangled particles, given that the universe is 13.8 to 14 billion years old?
I just mentioned communications, and this to me, and this is the most obvious thing, and you don't really need to have fiber optics or whatever.
You don't
it's
need
in real time. So if I flip this proton here,
the other one will
in
get
Jeddah, the other one will flip in I don't know, Riyadh, and it will be in real time. You will have real time communications.
The problem is that, realistically speaking, that other one is probably in the Andromeda galaxy.
But see, they actually developed this and they proved the quantum entanglement principle, I think last year, between the Canary Islands and France. So they actually developed an entangled or two entangled particles. But when I read about this slightly in depth, I think I'm not sure if you can use it for communications or if it's impossible or you have to develop it. There was an issue. And I think the issue was you can't actually, again, Heisenberg's uncertainty principle says that you cannot measure it and find its position at the same time. You cannot observe it and see its position at the same time. Which means you can only tell if one of the two particles has flipped if you observe the other one.
Yes.
So that kind of makes it difficult for communication, or you understand the concept? It's not that straightforward. It's slightly complicated, and the story is slightly bit more complicated.
But again, just as all things have developed, as long as we keep trying, we will eventually find something. And if we don't find it, we'll find something else. You see, Neil deGrasse Tyson says the next scientific breakthrough will not be a eureka moment, but rather a moment.
That's actually exactly how most scientists find their discoveries. They're like, that's funny. It's not usually a eureka moment. It's actually interesting. I didn't expect that.
Now let me just talk about one more thing, and then we could end it. I see that there's roughly 3 minutes left on the half hour.
No, we're actually 48 minutes right now running.
Okay. Oh boy. So last thing, you're still on the highway. Well, guess what? Maybe in another universe, you weren't on the highway. Maybe in another universe, you weren't even born. You see, the Copenhagen interpretation says that based on the three principles we just discussed, the universe splits at every instant into one of the infinite possibilities it can go into. The many worlds interpretation says that no, actually, it's just happening everywhere, and we just happen to be on the one in which we're following this particular timeline.
Interesting.
So that's parallel universes for you. They could exist.
I wish they do. And with that, I think we're done.
Wonderful.
Thank you, Abdulrahman. Wallahi.
Thank you very much for coming.
Very interesting.
Thank you for having
conversation,
me. It's been a
and
pleasure.
we would love to have you again.
I'd love to come back.
Inshallah. Are you based in Jeddah now, or are you going back to the States?
I am in Jeddah until further notice. So it could be a couple months, it could be a couple years, and who knows.
Okay, a wanderer.
I'm here indefinitely. Yes.
Okay. Thank you all for listening. Please check out Ilm FM on Comic-Con. We're going to be at Comic-Con Saudi في جدة on طريق الملك قدام in front of Red Sea Mall. And also this has been an experiment. هنجرب الإنجليزي.
Thank you very much for accommodating that, by the way.
قولوا لنا كيف نسويها. ماني عارف نترجمها وننزلها في نفس الحلقة ولا نترجمها وننزلها في حلقة مختلفة as in like an addendum or something like that, or عادي ما فرقت معكم.
نخليها زي ما هي.
قولوا لنا. أنا رامي طيبة.
وأنا ساري صبان.
وأنا عبدالرحمن لنجاوي or Lingo. Thanks for having me.
والسلام عليكم.
أنا خالد إيهاب من عمان الأردن. علم FM بتقديم رامي طيبة وساري صبان. تابعوهم على آيتونز أو ساوند كلاود، ابحثوا بالعربي على علم FM بدون همزة أو على مستثمر. وإذا عندكم أي تعليقات أو اقتراحات تواصلوا معهم على تويتر @ILM_FM واتركوا تعليقاتكم على الآيتونز.